So we're going to start here again by reading. Fred and Barney are at opposite ends of a 1 kilometer long drag strip in their matching race cars. Fred accelerates from rest toward Barney at a constant 2 meters per second squared, and Barney's already traveling toward Fred at a constant speed of 10 meters per second. So it's completely contrived, completely made up, simply for the purpose of giving you an example of this style of question. How much time elapses until they collide? So let's just say that Fred is over here and Barney's here. Would it work the other way? Absolutely, right? What is the actual question? How much time? We're solving for time. Now, they're going to collide somewhere there in the middle, right? Is it going to be right in the middle at 500 meters? No. How come? Well, it might be, I guess, right? But doesn't seem likely, right? This guy is accelerating, so he's going like 2 meters per second, 2 meters per second, 4, 6, 8, like he's going faster and faster and faster, and Barney's just sort of cruising along. So there's a good chance it's likely going to be somewhere over here, right?
Yeah.
Right at the 2/3 mark. Like, do we have any way of figuring out where? No. We do, however, know that the time when they collide is when they're in exactly the same position. Okay, so that's how we're going to do this. They will collide when they are in the same position. I'm just going to make a note of that. I was really just wasting time until Bea arrived because I didn't want to, I needed her to hear the whole thing. So, they collide when the positions are the same. They collide when their positions are the same. Pretty close. Okay, now, what is Fred's position at the start, at the beginning of the scenario? What's his position at? 0. P equals 0. What's Barney's position? Say again? 1,000, right you are. Opposite ends of a 1,000 kilometer long drag strip. So, let me just move this up here. Barney's position is 1,000. He converted the 1 kilometer meters, and we're going to say that this is the start, this is our reference frame, 0, and this is plus 1,000, right? Fred's position is forward or positive. Barney's displacement is negative, backwards. Okay, here's the part where I got to make sure I check this. Sometimes I get off on the wrong tangent here. Position Fred. 0. Position Barney. 1,000. They have to be equal to each other, right? Their positions have to be the same. So I'm going to write PF is equal to PB. That's when the crash occurs. Position Fred is equal to position Barney. Okay. Well, I mean, remember this is a sample, right? So I'm telling you that, right? How much time elapses until they collide? They have to be in the same place when they collide, don't they, Renee? Right? You might not think of it ahead of time, but do you understand it? Yeah, so you're good. Okay. So, Barney, or Fred's position as the time elapses, does he have a displacement? Yes, so I'm going to write that position of Fred is actually equal to 0 plus displacement Fred. And I'm going to write position Barney is actually equal to 1,000 plus displacement of Barney. Now, just sort of on the side here, what is Fred's displacement? Well, he is accelerating. So D equals, what do I know about Fred? From rest I know acceleration, but I don't know time, do I? But I can say VIT plus 1/2 AT squared. Initial velocity, 0, times whatever time gives me 0, plus 1/2 of the acceleration, which was 2, t squared. So in other words, Fred's displacement is 1/2 of 2t squared, which is 1t squared, or just t squared. Exactly. So over here in sort of my master one, position of Fred is 0 plus df will be, do I even need the 0? No, I just need, actually Fred's position is simply t squared. Okay, position Barney is a little bit different. Let's go over here. Displacement of Barney, dB. He's traveling at a constant speed, so his displacement then is actually just velocity multiplied by time, right? d bar t. So in this case here, he's moving at a constant 10, so his displacement is actually 10t. But there's one little tiny error that I made on purpose. In those two steps right there. It's pretty simple, and as soon as I tell you, you'll go, oh yeah, of course. I'll give you a hint. Which way is Barney going? So what's the velocity? Right? Right? Okay, so position, I'm just going to give myself a little bit more room here. So position of Barney is 1,000 plus the displacement, so in fact it's going to be 1,000, what? Minus 10t? Can you combine the 1,000 and the minus 10t? Give him a smack. Not in the head, though. No, you can't. In fact, what we're going to end up with here is what? T squared. The minus 10t goes to the other side and becomes 10t minus 1,000 equals 0. And what do we have to do? Quadratic equation. Well said, Renee. 10t squared plus 10t minus 1,000 equals 0. So we have to, there is no way around it. You must use the quadratic equation. X equals minus b plus or minus square root b squared minus 4ac all over 2a. Stay with me, Renee. X equals minus b is going to be plus 10?
No.
Yeah.
Oh,
Right here, right? Minus 10 plus or minus square root. B squared is going to be 10 squared minus 4. The a value is the number in front of the t squared, 1. The c value is minus 1,000, and it's all over 2a, which is 2 times 1. Let's just put 2 times 1 just so that we show that we've done it all. How many years have I been teaching? Is that what you said? How do you remember it?
23. You know the whole periodic table by heart?
No. What am I, some kind of nerd? Don't answer that. Not that there's anything wrong with that. Okay, so I got 10 squared is 100. I got minus 4 times 1, which is minus 4, times minus 4,000 is actually plus 4,000, and it's all over 2. And so you get x equals minus 10 plus or minus 100 plus 4,000 is 4,100. We're going to square root that. And that's the one number that I don't have written down. $64? Okay. Okay, so think a little bit here. If I go minus 10, subtract 64, I'm going to have minus 74 over 2. You're going to get minus 37. And if you go plus, it's going to be minus 10 plus 64. That's going to be 54 divided by 2, or 27 seconds. Does the minus 37 seconds make any sense, Shelby?
No, it doesn't.
A negative time?
It's weird.
No, it's weird. It's because you are every time you're dealing with a quadratic, right? You've got this kind of thing. There's the axis, right? So you got those two. But because time doesn't exist negatively, then that part of the equation doesn't really exist, right? So we just do this. So the time is, in fact, 27 seconds, which is like a lot of time, isn't it? It is a lot. Yeah. What if I asked you, where do they collide? Could you do that now? Why not now? You just assume you couldn't do it. Could you figure out where they collide? Sure, we've got their position is equal to 0 plus df, which is t squared, right? So in fact, it would be at position Fred is equal to displacement of Fred, because he starts at 0, which was equal to t squared, which is 27 squared. Should that number be less than 1,000? Should be. Someone help me out.
It's 390.
729. You should also be able to take that 27 seconds and plug it into here. Minus 10 times 27 is minus 270. From 1,000, 1,000 minus 270.
729.
How come it's not exact? There's obviously some rounding going on. So it's pretty close. Okay, so it's at a position of 729 meters. Let's go back and sort of look at the setup. Is the math here hard, with the exception of the quadratic formula? Not particularly. The hard part here is the setup. So let's have another look at, now that we know how it works, let's have another look at just how it works. Because guess what I'm going to do for the next example? I'm going to get you to try first. That's a really good question. We'll look at that too. Okay, so how did we set this up? The question was, how much time will elapse until they collide? So we have to make that jump, that logical jump, that they collide when their positions are the same. And we set position of Fred is equal to position Barney. And then we have to figure out an equation for that position of Fred. Fred starts at position 0, and his position then is 0 plus his displacement, which we figured out to be bit plus a half at squared. When we substituted, we ended up with just t squared. So I put t squared in for position of Fred. Watch again. Position of Fred, Renee, he starts at position 0. Is he moving forward? Yes. His position is the initial position plus his displacement. Right? His displacement is based on his 2 meters per second squared acceleration. What's his initial velocity? 0. So Fred's displacement is bit plus a half at squared. Initial velocity of 0 plus 1/2, his acceleration is 2. We don't know the t squared. 1/2 of 2 is 1. His displacement is in fact t squared, which I then put in for pf because his position is 0 plus df. Position of Barney, he starts at position 1,000. And because he's going backwards at minus 10, his displacement is minus 10 times t. Okay? Barney's position is his initial position of 1,000, subtract minus 10t. And then once I got that, it's a simple matter of throwing it all to one side and solving the quadratic. This works every time you've got two objects that have to be in the same place at the same time. Great question.
Yeah, I know. I was usually
Well, I would probably, you would probably get one for coming up with all that stuff over there, right? Basically, displacement t squared. You'd get one for that one there. You'd get one for basically telling me that they're equal to each other. Probably one for getting it to there. And maybe two, maybe one for the quadratic. Well, then this would be one more if I asked that, right? So 1, 2, 3, 4, 5, 6, 7. I think that's just a credit to where I got that picture from. Okay, so let's see if you can do this one kind of on your own. If you want to try it, go ahead. I would suggest you at least try it. You can always do the example on a sheet of loose leaf. Here we've got example 13. Jack is running at 6 meters per second to catch a bus. He sees it start to move when he's 20 meters away.
definitely not.
If the bus is accelerating at 1 meter per second squared, will Jack overtake it? Will Jack catch the bus?
Depends how fast.
If so, how long will it take it? It does depend on how fast he's running. He's running at 6. If Jack catches the bus, they are in the same position at the same time. Is the setup the same? Yes. In fact, it's exactly the same. There's only one small, tiny little difference. There is no negative. The bus is moving to the right. Good luck. Okay. Jack is running at 6 meters per second to catch a bus. He sees it start to move when it's 20 meters away. The bus is accelerating at 1 meter per second squared. Will Jack overtake it? And if so, how long will it take him? Once again, solving for time. Jack catches the bus when the positions are equal to each other. So when the position of Jack is equal to the position of the bus. Right? Maybe not that one, right? Okay. So what is Jack's position?
Drawing a line.
Jack is starting at a position of 0. The bus is starting at a position of plus 20. Position of Jack is going to be equal to, let's rewrite that so it's readable. Position of Jack is equal to his initial position of 0 plus his displacement, dj. He is running at 6 meters per second. That is a constant speed. How do you find the displacement of something moving at a constant speed? V bar times t. So in fact it's 0 plus V bar t times t. In other words, 6t.
So you're trying to find t, that's what you know, right?
No, all I know now is that the positions have to be the same for him to catch the bus, right?
6 isn't.
What is the displacement of a constantly moving object? It's moving at a constant speed, right? If you're moving at 100 kilometers an hour for 3 hours, how far do you go? 300 kilometers, right? 100 times 3. So the position of Jack is in fact equal to 6t. Okay, now do the same thing for the bus. The position of the bus is its initial position. Is it 0? No, it's in fact 20 plus the displacement of the bus. Right? It starts at 20 and then it's displaced. This one is accelerated, right? VIT plus a half AT squared. So it's going to be 20 plus VIT plus 1/2 AT squared Because it's accelerating.
Why did you put 20?
20 doesn't belong there. 20 is the distance.
Yeah, because this is position of the bus.
Why is it 20 at the right side?
Because it starts at a position of 20.
But then why did you put VIT? So like erase the VI. Because if you're saying 20 is the VI.
No. 20 is not the VI.
Oh, you're trying to find the whole thing.
Yeah, I'm doing the whole thing.
You're finding the ones
Right.
the DB. Not.
Right. Yeah, you're right. I think I did it slightly different than the previous one, right? The position of the bus is its initial position of 20 plus VIT plus a half AT squared. Its initial velocity, though, is 0. Right? The bus starts at rest. So this is, in fact, going to be 20 plus that 0. 1/2 of the acceleration of 1t squared. So 20 plus 0.5 t squared. Right? The bus's position is its initial position of 20 plus whatever its displacement is, which worked out to 0.5 t squared. And what am I going to do with that now? I'm going to put that right there, right? Okay, I'm going to let you guys solve it.
Is 0.5 T squared altogether?
Yep. Okay, so you need some help getting the quadratic formula set up. So to use the quadratic formula, one side has to be equal to 0. So let's set one side equal to 0. Does it matter which side? No. So 0 equals, put them in order, 0.5 t squared. Then comes the t, which is,
Oh yeah.
oh, hang on. I see. No, this is the plus, right? That's a plus sign.
Oh, that's on T.
That's a plus sign, yeah.
Oh.
You had me confused there 2%. That's a plus sign. So it's going to be minus 6t. That's why I put that little tail on the t. Minus 6t plus 20. So your A is let's finish it up. Excellent question, Shelby. So you should have, I'm going to rewrite the quadratic formula just because it's just a habit of mine. X equals minus b plus or minus square root b squared minus 4ac all over 2a. So minus b would be 6 plus or minus square root b squared is going to be 6 squared, which is 36. We can probably do this part, right? Minus 4ac, 4 times a, 4 times a half is 2 times the c, which is 20. So that's going to be, and 2 times 0.5. And Shelby's right. We got ourselves a problem. What does it mean when there is a negative discriminant? When the number under the square root is negative, what does it mean? This is actually a good thing because it means you can stop because the answer is no solution. Jack cannot catch the bus. There is no positive time value when these two are in the same position. Which is exactly what Joel did in a sort of a different way. Joel did this.
So where is the negative value?
Underneath the negative sign. Underneath the square root sign. You can't take the square, because that's going to be square root minus 4. Can you take the square root of a negative? No. Okay, this is what Joel did, I'm guessing. Joel said, Jack, bus, 6 meters per second. So that means in 1 second, Jack is at 6. In 2 seconds, he's at position 12. In 3 seconds, he's at position 18. And at 4 seconds, he's at position 24. Is this what you did, Joel? Kind of. He said the bus is, oh, I don't have how much the bus is accelerating. The bus is accelerating at 1 meter per second squared. This is 1, 2, 3, 4 seconds when he's at 24, right? If the bus is traveling at 1 meter per second squared, the acceleration, so 0, 1, 2, 3, 4. He starts at 0. His speed after 1 second is 1. His speed after 2 seconds is 2. His speed after 3 seconds is 3, 4. So after 4 seconds, he's going 4 meters per second. Is he going to be at position 24? If he's already going at 4 meters per second? He's going to be way past position 24. Jack has no chance. Now, Joel did that. You can use this as sort of a check, but again, if I change this to like 5.8, and I change this to like 20.3, and I change that to 1.75, there's no way you're going to be able to do it. Well, you could, but you wouldn't want to. All right, so you can use that as a check. This is the nice, easy way to do it. I know it doesn't look easy. If I'd shown you that in grade 11, it would have blown your mind. If I show you this at the end of the course, you'll go, yeah, no problem. Right?
So right now.
Just takes practice. It takes practice. You're not going to be good at it right at the start. It's not going to happen. Okay, now I think I gave you a bunch of textbook questions, did I not? Told you which ones? In that set, give me like 2 more minutes. Hang on, you guys. In that set of questions, there are a few of these kind of questions. There's not a whole lot of these going around. Okay? So you're going to have to find them. But make sure you practice them. There is, however, I created one on the back side of that pretest, right? There is no solution. You have to hand it to me and I mark it. It's a check to see if you know how to do it. I record it. It doesn't go towards your mark, so stop worrying about it. It's a practice.
If you hand it and say, I don't know how to do this.
Well, then I'm going to hand it back to you and say, go find some more. I'm not helping you with that one. That's practice. Okay, I'm done.